not even in the printing time.
All right, good. All right, I'm going to get started. Hey, everyone. So today I'm going to be talking about the coordination of distributed energy resources using a hardware-in-the-loop implementation. So basically, I'm currently a master's student. I'm working for Professor Alejandro. So I'm just going to give general outlines. So I'm going to start with the introduction, just a brief introduction of the stuff we do. Talk about frequency regulation, and I'll go into the system overview, the cyber layer, the physical layer, and then finally give the experimental results. So over the past few years, power networks have undergone a stark transformation, basically from the early days where you had generation at one end and load at the other to today where you have multiple generation points in the power network. So basically the proliferation of distributed energy resources has been the prime reason for that. And so basically you see the situation where we have intelligent electronic devices in the grid. And so basically these DERs, along with the random changes in the demand, have led to frequency fluctuations that are pretty much bad for appliances. So how do we rectify the issues involving frequency regulation? So the open market has ancillary services which are offered. And one of those ancillary services that are offered is frequency regulation. Frequency regulation offers the highest value. And basically how it works is that we use the effective integration and coordination of DERs to be able to make up for the frequency fluctuations that occur in the grid. So here I just have a basic diagram showing the difference between regulation and without regulation. So as you can see, you have some ripples that occur, which is bad for appliances. So for frequency regulation, basically frequency regulation occurs mainly by providing ramping up or ramping down of generation assets. Basically, if you know your basic power flow, you know that there's a relationship between frequency and real power. And basically that's the result of synchronous generators on the power grid. And so the PGM interconnection provides two regulation signals, the Reg A and the Reg D signal. The one that we're interested in is the regulation D signal. Basically, it's a high-pass filter signal that is basically an area control error designed for fast regulation units, which we're focusing on in this talk. So the Reg D signal corresponds to a required change in the power output that occurs every 2 to 4 seconds. And basically, the PGM has this compliance performance score that has to be greater than 75% to be able to partake in the market. So just to give a slight overview of how the performance score works, it's composed of 3 metrics. You have the delay score, you have the accuracy score, and you have the precision score. The delay score is pretty much about how quickly do your resources respond to the regulation signals that are received. And then you have the accuracy score, of course, corresponding to how well do your resources match the regulation that is required by the ISO. And then you have the precision score as well that basically measures consistency in your responses. And so here you just have a graph that shows the average performance score of both the regulation A and the regulation D signal. The regulation A signal is mainly for traditional regulation units, while the Reg D signal is for fast response units. And as you can see here, the regulation D signal has a higher performance, mainly because the regulation, basically the Reg D units basically have a faster response as opposed to the traditional regulation units. So I'm going to start by giving a system overview of our hardware-in-the-loop testbed. So basically what we have here is we have a computer here, and that computer is pretty much acting as the aggregator. In this case, the aggregator pretty much receives signals from the ISO, the regulation signals. And the job of the computer, which is acting as the aggregator, is to send these regulation signals to the leader node. In this case, the leader node is the one in orange. And basically, once the leader node receives those regulation signals, it distributes that signal accordingly among the other nodes in the network using the ratio consensus algorithm, which I'll talk about in more detail later. And then we also have the physical layer. The physical layer is pretty much a microgrid that is composed of 4 distributed energy resources. And those are all interfaced using inverters and are all connected to the bulk grid via a distribution line. And basically, when the ratio consensus is complete, we have reference signals that are sent to the DERs. And then these DERs have local power controllers that use this reference set points to determine the power output of the individual DERs. So I'm talking about the cyber layer. So our cyber layer hardware is comprised of 3 main parts. So each node has a microcontroller, Ethernet shield, and an XB module. So the XB module is mainly for wireless communication. And it's basically what allows us to be able to communicate and utilize the racial consensus algorithm. We have the Ethernet shield, which is basically there to provide communication between the nodes and the Typhoon Hill simulator. Basically, it utilizes a Modbus TCP protocol to send this via packet form to the Typhoon Hill simulator. And then, of course, we have the microcontroller, which basically is the base and performs local computation and constructs the packets that are sent accordingly. So this is just to give you a diagram of what our cyber layer hardware looks like. So over here, you have our XV device, and then the Ethernet shield, and then the microcontroller. These devices are stacked on top of the microcontroller, and the microcontroller provides the base of power source for the other two devices in the network, and it also deals with the construction of the packets which are sent to these devices. So in our cyber layer software, we have our controllers, and it has these algorithms and protocols which are necessary for the hardware testbed to work effectively. So basically, we have three main algorithms that we work with here. We have the racial consensus algorithm, which I'll talk about in the next slide. And basically, that's a distributed control algorithm that basically relies on the computation of two state variables in parallel. And then we have our clock synchronization. The clock synchronization protocol is necessary because the racial consensus algorithm needs to be performed in unison. So I'll also explain the clock synchronization protocol as well. And then finally, we have the Modbus TCP protocol, which basically allows us to send data between the controllers and the Typhoon Hill simulator. So for our racial consensus algorithm, we have two internal states, Y and Z. So basically, these two internal states are what make up the process by which we determine the global variable of our controllers. So as you can see here, we have two state variables, and these are updated per iteration. And basically, how it updates is it's a linear combination of a proportion of the state variables of the other nodes that are its neighbors, as well as itself. So you see here is a summation of the nodes that are part of its neighbors and as well as itself, and it takes a proportion of that according to its out degree. In this case, the out degree corresponds to basically how many nodes does the node in question talk to. So in this case, for example, if you had two nodes, if you had one node and you had two neighbors, in that case, the out degree would be 3 because you would be talking to two neighbors and itself as well. And then as well, you have the global variable that's calculated here, which is y divided by z. And basically, the goal here is that the way the racial consensus works is that after a long time, after sufficiently large k, you should have it such that all 4 nodes, or how many ever nodes you have in the network, all converge to the same value. So does anyone have any questions about the racial consensus itself before I move on to the next part?
What is that value?
Which one?
I mean, you said they all converge to the same value, which is written there. But
Yes.
Can you tell us what it is?
It's a global variable.
Right, but what is it?
So in a sense, it could be the regulation signal value.
No, but forget about the underlying application. So when you execute the algorithm, what is that quantity that each of the nodes are computing by taking the ratio of those 2 iterations?
Basically, it's a proportion of the total resource you have.
That's again, talking about the application. Just look at equation 3. What is their final result?
Okay, I see what you're saying now. Basically, it's the summation of their initial values divided by the initial values of y divided by the initial values of z, summed up together. So, yeah.
So why do you care about that as a frequency regulation problem?
Yes, so basically the goal here is that the regulation signal is only sent to one node, and then we use this algorithm to distribute that information from the regulation signal to the other nodes in the network. So for example, if your regulation signal was 0.5, we should pretty much say you want 0.5 of the amount of capacity you have. You want to provide that information. So 0.5 would be the y value of one node, and then it would be 0 for the rest for y. And then z would correspond to the capacities of each of the individual nodes. So basically, when you calculate that and determine the global variable, you see that it corresponds to the proportion based on their ratings.
And also, you can also use it if you're trying to compute frequency error in a microgrid, because the y iteration would be frequency mismatch that everyone is measuring locally, and then the denominator would be 1 or whatever you want to initialize it to. It could be like also weighted average. So then what they end up computing at the end is just the average frequency error. And you have a quadratic program for the economic dispatch with quadratic constraints, with quadratic cost functions. If you write the Lagrange dual, you can show that the solution which you can compute yeah, some interpolation, you can write it as ratios of sums of things that the nodes have. So again, they can use this algorithm to compute those quantities to get a distributed solution to that problem.
So here I'll talk about the clock synchronization protocol. So the reason why the clock synchronization is necessary is because you basically have two variables that you're trying to update at the same time. So in order to ensure that those variables are updated accordingly, you need to make sure that all nodes in the network are in sync or they have the same common time reference. So how is this done? Basically, this is a three-step process. What you have first is you have node 1 send a time, basically sends a time t1 a packet to node 2, which records the time that it receives that packet. And then after it receives that, you have this equation which corresponds to D1 being the message propagation delay, and you have D2, which is the local clock offset between node 1 and node 2. And then you have node 2 send an acknowledgement packet back. So when it sends the acknowledgement packet, it knows the time it sends that packet and includes that in the packet it sends. And then when node 1 receives that packet back, then it records the time that it received the packet, which is T4, and it has this equation here. And so having these two equations and having two unknowns, you're able to determine what the message propagation delay is, as well as the local clock offset between node 1 and node 2. So this is just showing an illustration of the process. Basically, you have node 1 starts it, and then back and forth until you get calculate D1 and D2, and then that's distributed accordingly to node 2. So in our case, because we're working with more than a 2-node system, we have 4 nodes in our network, for example. So basically, you want to have a way to be able to determine a common time reference for 4 nodes. So how do we do that? So in this first step process, instead of you just sending one packet to one node, you would have node 1 broadcast the packet to all the other nodes in the network. And then once you broadcasted that packet, they all know the time that they received the packet. And then it chooses one target node in particular to be the node 2 in this case, and then send the value back to node 1. And then once it calculates D1 and D2, it then sends those values to all the other nodes in the network. So I'm just going to give a brief overview of the physical layer. So basically what we have here is basically you have distributed energy resources such as PV units, and you know that they're interfaced by an inverter. So in this case, the inverter is comprised of a 3-phase inverter, the LCL filter, the power controller, and the phase lock loop. So basically the phase lock loop is there because you want to kind of have a consistent phase angle, and then the power controller uses that reference that you sent via the ratio consensus to determine the set points for your voltage, which determines what your inverter sets to deliver the set amount of power. And so in the case of our application, we have a microgrid which is composed of 4 distributed energy resources. So basically we have 4 inverter models defined, with each one having their own power controller and phase lock loop. So in terms of experimental results, first of all, you have a setup such as this, where you have 4 nodes, 4 distributed energy resources, each with having their own assigned capacity. And so with that information, you have this ring communication graph set up here, and basically that's how they would communicate using the ratio consensus algorithm. So basically just showing the results, just to give more interpretation behind what these values mean. So the initial values of Y correspond to, so 0.5 is basically the regulation signal, and Z corresponds to the capacities of the individual distributed energy resources.
So the lower limit capacities here are 0, right?
Yes. Yes. And so basically you have it such that this is what should be expected. They should converge to the result 0.5 here, which is the summation of their initial values divided by each other. And here you see that process happening. So basically each one here corresponds to the gamma of each node in the network. And you see here that after some time, they eventually converge to the appropriate value, which is 0.5. And so I should have mentioned this earlier, but we have a robust ratio consensus. So the initial ratio consensus algorithm has a problem where that if you have packet drops, there's a possibility of convergence to an inaccurate solution. So in order to make up for that, we have a robust ratio consensus which accounts for those packet drops. So instead of you just taking the updated values, you sum those up accordingly so that even if you miss them at one iteration, you can always get them back in the next iteration. And so here I just give an overview. So this is basically a 40-minute time slot. And basically what we have here is we have 4 distributed energy resources tracking the regulation signals over a 40-minute interval. Every 4 seconds, it changes to a new value set point. And you see how the different distributed energy resources adjust their output accordingly based on the regulation signal. You notice here that the red one, which corresponds to DR power output, is lagging behind a little bit behind the regulation signal, which makes sense because the ratio consensus algorithm itself takes a certain amount of time to compute. So in our case, it takes around 45 seconds to compute. So that's what leads to this delay occurring here in the plot shown. So thanks for listening. Anyone have any questions?
I have a quick question.
Yes.
So you are, so it's perhaps philosophical.
Mm-hmm.
You have a particular regulation signal coming in,
Mm-hmm.
and you're disaggregating it across a collection of distributed energy resources.
Mm-hmm.
Suppose I don't pay attention to this ratio stuff, but all I want to do is that the total thing adds up to that value,
Mm-hmm.
as opposed to doing it proportional to their capacities.
Mm-hmm.
What is the relative advantage?
So are you saying what could you do except for doing the capacity one?
So I want them to add up to that DER, to that regulation signal.
Mm-hmm.
X1 plus X2 plus X3 is equal to the regulation signal that you send.
Yes.
And X1 has to be less than or equal to its capacity, X2 is less than or equal to capacity, X3 is less than or equal to it.
Yes.
But I don't divide them according to their ratio of their capacities at all. I don't pay attention to that. I just disaggregate in a way where the summation is equal to this.
Well, you have to have some metric to determine how you distribute the resources, though.
Yeah. So the
The
point
resource.
is, the ratio consensus comes with its own requirements and stuff, right?
Yes.
So I can bypass that and just do something where the summation of xi is equal to whatever. Let's say I need 10 kilowatts of change.
Mm-hmm.
X1 plus X2 plus X3 is 10, and each individually X1, X2, and X3 is less than or equal to some whatever their individual capacity. So I don't pay attention to the
Mm-hmm.
to any sort of
Yes.
reasoning
Requirement,
why
yes.
each one should be this way, why it should be this way, why it should be that way. Is there anything that insights you can provide?
All I can say is that we've worked on another paper where instead of distributing the resource based on their capacities, we distribute them based on to minimize the losses in the system. So basically, we have distribution lines with certain power losses, and thus at the microgrid to the bulk grid connection point, we have a certain amount of power that is less than expected. So basically, instead of doing it that way, we do it in a way such that we optimize the amount of power that goes out to the bulk grid such that it matches the expected. So in that situation, what makes that different is that instead of having the capacities, it's more of an optimization problem where we determine Y and Z accordingly.
The motivation behind asking this question is that when it's just a pure summation because there is no network constraints, then there is still some rationale because it's done proportionally in such a way that it pays attention to the capacities. Then you will lose if one resource goes out.
Yes.
It goes proportional to its capacity in the network. So that makes sense, but I don't know how it works out when there's a network and that has its own constraints. Then does ratio consensus make sense in disaggregation?
That's a good point. Professor Andrew, any?
As I was saying earlier, ratio consensus is a primitive for solving many of these coordination problems. So what he was doing here, just a simple version of what you can do, which is you have no network constraints. So what you can do is just allocate proportionally, so that's per splitting, and that's actually also minimizes the deviation from the average, I think it is. But in the case of if you have network constraints, or underlying network, as he was saying, you can capture that via losses. You have a linear program, and then you can show via the Lagrange dual that you can recover a solution in a distributed way using ratio consensus, because it's just a primitive to doing calculations of ratios of sums. That's the philosophy, that ratios of sums seem to appear in many of these problems. You can decompose solutions as ratios of sums. So we just use it as an artifact to do that calculation distributively.
Anyone else have any questions? Alalu? Siddharth? Yes.
So what will result in present is it a simulation or did you actually implement a hardware?
It's actually implemented in hardware.
Was it related to the lab you're setting up in 4024?
That's the future, yes. But when I did it, it was just on my desk with the controllers and the Typhoon Hill and all that, yes.
So you have a related question to that. So you
Yes.
have your microcontroller
Yes.
as a physical
Yes, as a physical.
And your
It's-
rest of the system is simulated.
The Typhoon is a hardware-in-the-loop simulator. So in a sense, it's more of a higher fidelity resolution model stuff. So basically, the simulations are more in terms of what would happen in real life,
And
per se.
what's the sampling frequency for those simulation models?
So the simulation step is 2 times 10 to the minus 4. So in 200 microseconds.
200 microseconds.
Yes.
And then your switching frequency for your control loop is also 200 microseconds?
No, I can't give you much details on the controller frequency though. The inverter frequency, that's what you're asking, right? The switching frequency for the
So 200 microsecond is your time step for your
simulation state step. Yes.
in Typhoon.
Yes.
And what's your control loop frequency? So your microcontroller is controlling how often does it send control signal?
I think I can't remember actually right now what the frequency of the
There are two controllers there, right? One is the higher level control, which is what actually is implemented in hardware, and then there are the lower level controls of the inverters, which those are part of the simulation.
Okay, so this inverter simulation is still in the software.
Inverter simulation is 100% software, meaning the physical, I mean the circuit, the power circuit plus the controls, they are all simulated. The inner voltage control, the inner current control and the voltage, that's all simulated. And then on top of that, there is a system level control, which in this case, it's sending signals to the inverter every 2 or 4 seconds. Oh, so that's basically, no, 2 to 4 seconds.
2 to 4 seconds.
Right, because it's a regulation signal, right? So that's what the inverter is trying to track.
So this algorithm is in the microcontroller,
That's
which
right.
is at a higher level. It's not primary control, it's tertiary control, if I say.
You want to call it tertiary control from the point of view that you are calling primary control the inner current and voltage. Although for us that would
it's
be
more of
primary
a
control.
Okay, fine.
Yes, that's the right idea. And
Yeah.
the other two controls, what you call primary and secondary, they are still simulated. Yeah. You could push those out of the emulator, have them sitting in an industrial grade controller, and that interface on top of what we have as well. So this would be. So right now, this is the hill which has the power stage plus lower level control. And then the box he showed there, it's basically talking to this guy. There are several of these. Each of them controlling one of the resources, and then they are talking to each other wirelessly. Okay? I mean, and then what you could still do is push this out, have the lower level control here, and this being implemented in hardware.
So from an implementation perspective again, like how easy it is to have this wireless communication going on. So how big can my grid be?
That depends on the size of the grid. So I guess you just said that. So the convergence rate of the algorithms is determined by the size of the grid, and it's more like the connectivity of the grid actually. Because even if you have like a large grid, if everyone talks to everyone, then the algorithms we have will converge exactly one step. It's just all to all, right? So it's the convergence rate is based on you can characterize the second largest eigenvalue of some matrix we have there, or you can also get some feeling for how fast it's going to converge based on the diameter of the graph, which is defined as the largest of
the shortest path from one. Yeah.
Between any two noses, right?
Yes.
Yeah.
It's the largest part between any two nodes.
Largest path. No.
Yeah. Largest path. Yeah.
So that gives you a feeling. Yes, that's right. So things like if you have like a linear network like this is pretty bad in terms of convergence, even if it's a small system. Okay. Right. So that would basically tell you how long it will take for the algorithm to converge. But then you have the algorithm is iterative in nature, and then you have each of the iterations is 20 milliseconds. And then let's say that the network is such that it'll take you like 10 iterations for this to converge. So that means that you have 10 times 20 milliseconds, that's 200 milliseconds. And we are talking about signals that need to be followed on a 2 to 4 seconds basis. So that's probably reasonable.
Okay. And if you don't have a wireless communication, instead you have a Ethernet like network, will it change the game plan or any of these controls?
You might be able to push the iteration step.
It won't really change. I feel like in that case it would be fully connected, fully connected, and in that case it would be done in one step.
Right. So what Sam is saying is that you could have basically a ring network, and then everyone has access to all the information, so it's an all-to-all communication.
And then there is no question of convergence.
Yes.
Trivial.
Are you guys also looking at what happens if one of these communication bridge fails?
Yeah.
Yes.
That's actually, I mean, one link going down is not a big deal as long as you can detect it, which is relatively straightforward. What's important is what about if these links coming in and out, and that's what he was saying. If you have packet drops, because that's really what's problematic. Okay, because then the algorithm, what the ones that show the basic version won't converge. But we have a robustified version that even if you have like those packet drops, you still converge. And even synchronization errors. I mean, there is an underlying assumption here that all nodes are synchronized at the granularity of the iteration, whereas that's not the case in practice. But again, the robust version also works in that case.
Thank you. Sorry if I hijacked all your questions.
No, that's fine.
Okay. I think you have a.
I was going to ask, can you comment on the delay you pointed out? Slide 23.
Oh. Yes.
You said there was a delay between the ready signal and the response.
Yes. So when I mean when the ISO sends to the aggregator regulation signal, there's a certain time between when the amount of time the rich consensus takes and then actually updating the value. So basically, that regulation signal you see there corresponds to the regulation signal received by the aggregator, and then the time it takes for rich consensus to complete and eventually send the results of that to the local controller to update the set points accordingly. So is that good?
Yeah. How does the delay compare with the requirements from the system operator?
How so?
You talked about a performance score earlier.
Yes. So basically, I mean, the longer it takes for your units to respond to the change in the power output, I mean, the worse that is, I mean, the longer it takes, basically, the worse your score will be, if that makes sense. Okay. All right. Yes.
So each DR is implemented in the HIL.
It's a combination. So we have a hardware controller that is on the outside. So basically, this is a physical controller. And then you have a local power controller that is modeled inside of the Typhoon Hill simulator. So the DR has basically two components, one that's physically existing and one that is simulated.
So in the HIL part,
yes.
it's a set of linear differential equations.
Yes.
What was the order for that equation?
No, I'm saying it's not linear. It's a full-blown model of the system. So the switching transients are involved.
Switching is even involved.
Yeah. Okay. All right. Thanks. Anybody else have any questions? All right. I think we're good. All right. Thank you.